तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the second lecture of Module 9. In this lecture, we shall study one-way slabs. First, we shall learn about the different types of slabs, and then we will move on to the analysis and design of one-way slabs. Slabs are an important structural component where prestressing is applied. With increase in the demand for fast-track, economical and efficient construction, prestressed slabs are becoming popular. In the present module, the slabs will be presented in two sections, one-way and two-way slabs. Rectangular slabs can be divided into two groups based on the support conditions and length to breadth ratio. In the first type, when a slab is supported on two opposite edges, then it is a one-way slab spanning in the direction perpendicular to the edges. Precast planks fall in this group. A ribbed floor, which means slabs with joists consisting of double T sections, and a hollow core slab are also examples of one-way slab spanning in the direction. In the second type, when a rectangular slab is supported on all the four edges and the length to breadth ratio, which we shall denote as L by B, is equal to or greater than 2, the slab is considered to be a one-way slab. The slab spans predominantly in the direction parallel to the shorter edge. Thus, see, the first type of one-way slabs is supported only on the two opposite edges. In the second type of one-way slab, they are supported on all the four edges, but the length to breadth ratio, where length is the larger horizontal dimension, breadth is the smaller horizontal dimension. When this length to breadth ratio is greater than or equal to 2, then also the slab is considered to be one-way slab, and the slab spans in the shorter direction. A slab in a framed building can be a one-way slab depending upon its length to breadth ratio. A one-way slab is designed for the spanning direction only. For transverse direction, a minimum amount of reinforcement is provided. Thus, given a building plan, first we have to determine whether a slab is one-way or not depending upon the length to breadth ratio, and if they are supported on all the four sides. Now, if we determine that a slab is one-way slab based on the criteria that the length to breadth ratio is greater than or equal to 2, then we design the slab only for the spanning direction. For the transverse direction, we provide only minimum amount of reinforcement. In this figure, on the left side, we have a slab which is spanning from left to right, and because it is supported only on the two edges, whereas for the slab on the right side it is supported on all the four edges, and here the length is greater than or equal to the breadth, and the slab is spanning in the shorter direction parallel to B. Other types of rectangular slabs and non-rectangular slabs are considered to be two-way slabs. If a rectangular slab is supported on all the four sides and the length to breadth ratio is less than 2, then it is a two-way slab. If a slab is supported on 3 edges or 2 adjacent edges, then also it is a two-way slab. A slab in a frame building can be a two-way slab depending upon its length to breadth ratio. A two-way slab is designed for both the orthogonal directions. That means whatever types of slabs which are not falling under the category of one-way slab comes under two-way slabs. For rectangular slabs, if the length to breadth ratio is less than 2 when all the sides are supported, then it is a two-way slab. And for a two-way slab, it has to be designed for both the orthogonal directions. Again, given a building plan, first we have to identify whether a slab is a two-way slab or not, and then we have to proceed as per the two-way slab design. Now, in this module, we shall focus only on the one-way slab analysis and design. A slab is prestressed for the following benefits. First, it is the increased span to depth ratio. Typical values of span to depth ratios in slabs are given below. For non-prestressed slab, the span to depth ratio is 28:1. For the prestressed slab, it is 45:1. That means here you can see that a prestressed slab can have a larger span compared to its depth, and this is a big benefit when we are looking for large column free space. Thus, one very important aspect of prestressing a slab is to increase the span to depth ratio. The second benefit is the reduction in self-weight. Once the self-weight is reduced, the design of the supporting beams or columns are also lead to smaller sections. The building mass is reduced, it leads to lower seismic forces, and we get a tangible benefit from the prestressing of the slabs. The third benefit is sections remain uncracked under service loads, and this leads to increased durability. Durability is of a concern wherever we have exposure conditions worse than moderate, and if the slab is uncracked, then we have increased durability. The fourth benefit is it's a quick release of formwork. Once a slab is prestressed, the formwork supporting the green concrete can be removed quicker because the concrete can sustain its weight due to the effect of prestressing, and hence this leads to a fast track construction. The fifth benefit is the reduction in fabrication of reinforcement. In conventional slabs, the reinforcement is by ordinary steel. It needs more time to place and tie the reinforcing bars, whereas in prestressing slabs, it is the prestressing strands are either placed in a precast yard or the post tensioning is done in strands which are placed in ducts, and both these operations are faster than the conventional fabrication of a reinforcement cage. And the sixth benefit is more flexibility in accommodating late design changes. Thus, once a design has been made for a particular utilization of an area, if the client needs some change in the utilization of the floor space, the column free space has greater flexibility to accommodate that change. Although we have the benefits of this prestressing of slabs, we have to be careful that the analysis, design and construction has to be done carefully, and the quality of construction also has to be strictly adhered to. Precast planks are usually pretensioned. They are manufactured in an yard under controlled environment, whereas cast in situ slabs are usually post-tensioned. Post-tension slabs are becoming popular in office and commercial buildings and parking structures, where large column free spaces are desirable. The maximum length of a post-tension slab is limited to 30 to 40 meters to minimize the losses due to elastic shortening and friction. That means that although theoretically we can go for even larger spans, but since we have elastic shortening of the slab and there is loss due to friction, usually the post-tension slabs, the spans are limited to 30 to 40 meters. Slabs can also be composite for the benefits of reduction of formwork, cost and time of construction. The quality control is also better in a composite slab. A precast plank can be prestressed and placed in the final location. A topping slab is overlaid on the precast plank. The grades of concrete in the two portions can be different. This figure shows a precast plank where the bottom part has been precast and prestressed in the yard. These are the prestressing ducts, and the top part is a cast in situ topping where there has been some reinforcement to consider the effects of temperature and shrinkage, and the combination of these two is called a composite slab. That means the bottom part is precast and prestressed, whereas the top part is cast in situ. Next, we are moving on to the analysis and design of one-way slabs. One-way slabs are analyzed and designed for the spanning direction similar to rectangular beams. The analysis and design is carried out for the width of the plank or a unit width, say 1 meter of the slab. Ribbed floors are designed as flanged beams. Thus, whatever we had studied for the design of beams, they are also applicable for the design of one-way slabs. The slabs are designed based on their width if it is a precast plank, or it will be designed for a unit width, say 1 meter, and the analysis and design procedure for one-way beam is applied for the one-way slabs. If the one-way slab is a ribbed floor, then we have to apply the analysis and design procedure for a flange section. For continuous slabs, the moment coefficients of IS 456-2000, which are given in table 12, can be used. That means in the conventional analysis, if it is a simply supported slab, we use the conventional structural analysis formulae. But if it is a continuous slab, then we can use the moment coefficients that is provided in IS 456-2000. We do not need to go for a rigorous analysis. The analysis and design procedures for simply supported rectangular beams are covered in the modules analysis of members under flexure and design of members for flexure respectively. These materials are briefly reproduced here. Earlier, in module 3 and module 4, we have studied the analysis and design procedures of beams in details. Here, we are revising them briefly. First, we do a preliminary design, and in the preliminary design, first the material properties are selected. That means FCK, which is the characteristic compressive strength of concrete, and FPK, which is the characteristic tensile strength of the prestressing steel, are selected. Before starting a project, the grade of concrete and the type of prestressing steel is fixed during the contractual process, and from that we know what are the values of FCK and FPK. Second, determine the total depth of the slab, which we shall denote as H, based on the span to effective depth ratio given in clause 22.6 of IS 1343/1980. The span to effective depth ratio will be denoted as L by D, and this ratio is limited to avoid deflection computations. If we fix our total depth satisfying this span to depth ratio, then we do not have to check the deflections of the slab if the load is conventional. Now, in order to relate the effective depth with the total depth, we can use an approximate estimate that D is about H minus 25 millimeters. And once we select D based on the L by D ratio, we can select H, and then we have to round off H to a multiple of 10 millimeters. Thus, the total depth of the slab is determined based on the deflection requirement. Next, we calculate the self-weight of the slab. Once the depth is known, the weight per unit width of the slab can be determined, and then we calculate the total moment, which we are representing as MT, including moment due to self-weight, which we are representing as MSW. So once we have been able to calculate the self-weight, we add that to the other dead load moment and live load moment to get the total moment MT. After this, we estimate the lever arm, which we are denoting as Z. Z is equal to 65% of the total depth, that is 0.65 H, if the self-weight moment is large. Say the self-weight moment is greater than 30% of the total moment. If the self-weight moment is small, then we can estimate Z to be about 50% of the total depth, that is Z is equal to 0.5 H. These are rough estimates of the lever arm by which the compressive force will move up from the CGS under service conditions. The sixth step is estimate the effective prestress, which we shall denote as PE. PE is equal to the total moment MT divided by Z if the self-weight moment is large, or else PE is equal to the moment due to imposed loads, which we are denoting as MIL, divided by Z if MSW is small. These are some rough guidelines to estimate the prestressing force given the moment and an estimate of the lever arm. Here, the moment due to imposed loads is given as MIL is equal to MT minus MSW. That is, it is the moment due to the superimposed dead load and the live load. How are we calculating that? we are subtracting the self-weight moment from the total moment, and we are saying that that is the moment due to the imposed loads. In the 7th step, we are considering that the effective prestress is about 70% of the characteristic strength of the prestressing steel. From that, we are calculating the area of prestressing steel. AP is equal to PE divided by FPE. Thus, first we have estimated the effective prestress, we have estimated the effective prestressing that in the tendons. From there, we are having an estimate of the amount of prestressing steel for the chosen width of the slab. In the 8th step, check the area of cross section A, where A is equal to 1000 times H. 1000 is the width of an 1 meter wide slab, and H is the total depth. The average stress C divided by A should not be too high as compared to 50% of FCC allowable. C is equal to the effective prestress PE. Thus, we are saying that the average prestress over the cross section, which is given as C by A is equal to PE by A, should not be larger than 50% of the allowable compressive stress for the concrete in the slab. With these steps, we have found a preliminary design of the unit width of the slab, and then we are moving on to the final design, where we are checking the stresses in the slab under the service load conditions. The final design involves the checking of the stresses in concrete at transfer and under service loads with respect to the allowable stresses. The allowable stresses depend on the type of slab, type 1, type 2 or type 3. Here the steps of final design are explained for type 1 slabs only. For type 1 slabs, no tensile stress is allowed at transfer or under service loads. Thus, the steps of the final design primarily consist of checking the stresses in the sections at transfer and under service conditions. Now, the allowable stresses depend on the type of prestress member that we are designing for. Earlier, we had known that the prestress members are divided into 3 types. Type 1, where we do not allow any tensile stress either at transfer or during service. Type 2, where we allow tensile stresses but we do not allow cracking. And type 3, where we allow cracking but the crack width is limited. In this section, we are studying only the design of type 1 slabs. The design of type 2 and type 3 are very similar to the design of type 1 slabs, the difference being we have to incorporate the allowable tensile stress in the expressions. This was covered in details in the analysis and design of beams. For small moments due to self-weight, say when MSW is less than 30% of the total moment, the steps are as follows. First, calculate eccentricity E to locate the centroid of the prestressing steel. Here we are doing an accurate calculation, and what we are first doing is we are trying to locate the centroid of the prestressing steel with respect to the centroid of the concrete, the CGC, and this distance between the CGS and the CGC is denoted as the eccentricity E. The lowest permissible location of the compression due to self-weight is at the bottom kern to avoid tensile stress at the top. Earlier, we had studied about these kern locations, that the kern points are those that if the compression is at those points, then there will not be any tension in the section. Thus, when the slab is under minimum load, that is when it is only under its self weight, the lowest possible position of the compression is the bottom kern point. The distance of the bottom kern point from the CGC is denoted as KB, and if we base our design based on this bottommost position of C, then we get an economical section. The design procedure based on the extreme location of C gives an economical section. In this figure, we are studying the stress conditions. H is the total depth of the slab. First, at prestressing, the compression is at the same location of the CGS. Then, as the self weight acts, the compression moves up from the CGS, and it has to be within the kern zone to avoid any tensile stress in the section. The lowest possible location of C, that means the minimum that C has to travel up from the location of CGS, is up to the bottom kern point, which is at a distance KB from the CGC. And here E is the distance between the CGC and CGS. This figure shows the internal force in concrete due to the self weight of the slab. And the stress condition is that when the C is located at the bottom kern point, the stress at the top is 0, and the stress at mid height, which is the average stress, is given as C by A equal to P0 at transfer divided by A, and the stress at the bottom is denoted as FB. This is the stress diagram throughout the depth of the slab due to its own weight. From the stress profiles, the following equation can be derived. E is equal to MSW divided by P0 plus KB. The derivation of this expression was shown earlier. Again, here we are recollecting this expression of E, which gives us the location of C at the bottom kern point. And this is a function of the self weight of the moment, the prestressing force at transfer P0, and the distance of the bottom kern point from CGC. The magnitude of C or T is equal to P0, the prestress at transfer after initial losses. Thus, by this equation, we are able to determine the lowest possible location of the centroid, and this will lead to an economical section. The value of P0 can be estimated as follows. P0 is equal to 0.9 pi, that means 90% of the initial pre-stress for pre-tension slab, and it can be 100% of the initial pre-stress for the post-tension slab. In the pre-tension slab, due to elastic shortening, P0 is lower than Pi. Here Pi is the initial applied pre-stress, and the maximum value of Pi is equal to 80% of the characteristic strength times the estimated area of the pre-stressing steel AP. The permissible pre-stress in the tendon is 0.8 FPK, and this is used to find out the maximum initial pre-stress that we can apply on the estimated amount of pre-stressing steel. Now, once we have determined the eccentricity, next we are recomputing the effective prestress PE and the area of prestressing steel AP. This is based on the stress diagram under service conditions. Under service conditions, due to the total moment, the maximum distance the C can traverse is up to the top current point. At this location, the stress at the bottom is 0, the stress at the top is Ft, and again the average stress at mid height is C by A equal to PE by A. This is the stress profile under service conditions. And based on this stress profile, the shift of C due to the total moment gives an expression of PE. And the derivation of the equation was shown earlier, and again here it is recollected that from that stress profile we get PE is equal to the total moment divided by E plus KT, where E plus KT is the distance by which C has traversed from CGS to the top current point. For solid rectangular slabs, KT equal to KB equal to H by 6. Thus, the top and the bottom current points are located at 1/6 of H from the CGC. Now, once we have calculated PE, next we are recomputing the amount of prestressing steel. Considering again that the effective prestress FPE is equal to 70% of the characteristic strength FPK, the area of prestressing steel is recomputed as follows. AP is equal to PE divided by FPE. The number of tendons and their spacing is determined based on AP. It is given the value of PE, given the value of FPK, we are calculating the amount of prestressing steel that we need for the unit width or whatever width we have selected for the slab. And once we calculate AP, we can distribute that in the tendons with suitable spacing. And with this, we know the amount of prestressing force under service conditions, and we can update the value of prestressing force at transfer. Once we have updated P0, we can recompute E again with the updated values of AP and P0. Thus, you have to appreciate that the design is a sequential process, that you compute some variables based on some estimated quantities, and then again you recompute the estimated variables, and like that you converge to a result which is suitable regarding the stresses and the layout of the prestressing tendons. If the variation of E from the previous value is large, another cycle of computation of the prestressing variables can be undertaken. For large self-weight moment MSW, if E violates the cover requirements, E is determined based on cover. See, the expression of E that we have written was determined based on the force conditions, but if the self-weight moment is high, then E may come out to be large and we may violate the cover requirements for the prestressing tendons. In that case, the E is selected based on the cover requirements, and then we check the amount of prestressing steel and the prestressing force. In the fourth step, we check the compressive stresses in concrete. At transfer, the stress at the bottom FB is equal to minus P0 by A, which is the average stress, times H divided by CT. This is equal to minus 2 P0 by A, because H is equal to 2 times of Ct. Thus, we are able to calculate the stress at the bottom based on the designed prestress at transfer and the properties of the section. The stress at the bottom Fb should be less than the allowable compressive stress FCC allowable, and this can be expressed as an equation that the magnitude of Fb should be lower than or equal to FCC allowable. Next, we are checking the compressive stress in concrete at service conditions. The expression at the stress in the top is similar, that Ft is equal to minus Pe by A, which is the average prestress, times H by Cb. This relationship is again coming from the triangular stress distribution, and this is equal to minus 2 Pe by A, because H is equal to 2 times of Cb. The stress at the top Ft should be less than FCC allowable, where FCC allowable is the allowable compressive stress in concrete at service. And here also we are expressing this relationship as the magnitude of Ft should be less than FCC allowable. Note that the allowable compressive stress at transfer and the allowable compressive stress at service are different. For type 2 and type 3 members, the tensile stress should be restricted to the allowable values. So, when we showed this design for type 1 members, the allowable tensile stress was 0, but if we do the design for type 2 and type 3 members, then the allowable tensile stress is as per the values given in the code. For a continuous slab, a suitable profile of the tendons is selected. This is covered in the module of cantilever and continuous beams. So, the value of eccentricity that we have found is at the critical location. For a simply supported beam, the critical location is at the middle. We can have a parabolic profile, or if the depth is small, then we can have a straight profile with constant E. For a continuous slab, the prestressing tendon goes above CGC at the support locations, and then we need to determine several values of the eccentricity, one at the span, another at the support, and this procedure was shown in the module of continuous beams. And for the continuous beams or slabs, the important design element is selecting an appropriate profile of the tendons. When the value of E is fixed, say in either pre-tension or post-tension operations, the design steps are simpler. If the tendons are placed at the CGC, say for which E is equal to 0, then there is uniform compressive stress due to prestress, which counteracts the tensile stress due to service loads. Sometimes the eccentricity is fixed based on the construction requirement. If the eccentricity is 0, that means the CGS lies at the CGC. In that case, there is a uniform compression in the slab, and this uniform compression counteracts the tensile stress that is generated due to the bending. To have 0 stress at the bottom under service conditions, the value of Pe can be directly calculated from the following equation. Pe by A, which is the uniform compressive stress, is equal to Mt divided by Zb, which is the tensile stress generated due to the bending under service conditions. From this, we directly get the value of the prestressing force, that Pe is equal to A times Mt divided by Zb. this expression is a simpler expression which we can use if the eccentricity is 0, and this is based on the concept that the compressive uniform compressive stress balances the tensile stress under service conditions due to flexion. ZB is the section modulus. The above expression is same as PE equal to MT divided by KT, which is equation 9b3 with E equal to 0. Earlier we had seen one expression where PE is equal to MT divided by E plus KT. In that equation, if we substitute E equal to 0, then we get PE is equal to M divided by KT, and this expression is same as PE equal to A times MT divided by ZB. Thus, both these expressions are same, but the one given here is a convenient expression when the eccentricity is 0. The stresses at transfer can be checked with an estimate of P0 from PE. That means once we have calculated PE, we can estimate P0 from PE, and based on P0 we can calculate the stresses at transfer. The fifth step is to check the shear capacity. The shear is analogous to that generates in a beam due to flexure. The calculations can be for unit width of the slab. The critical section for checking the shear capacity is at a distance effective depth d from the face of the column or the supporting beam across the entire width of the slab. The critical section is transverse to the spanning direction. Thus, for one-way slabs, the checking for shear is similar to beams, where the critical section is considered to be at a distance effective depth from the face of the support, and the critical section is perpendicular to the spanning direction. The shear demand Vu in the critical section generates from the gravity loads in the tributary area. That means once we know the tributary area for the slab, we can calculate what is the shear demand that comes in the critical section. For adequate shear capacity, the resistance VUR should be greater than VU, where VUR is equal to VC, the shear capacity of uncracked concrete of unit width of slab. We do not usually provide shear reinforcement in slabs. Thus, the shear capacity is equal to the shear capacity of the concrete for uncracked section. The expression of Vc is given in the module of analysis and design for shear and torsion. If this is not satisfied, it is preferred to increase the depth of the slab to avoid shear reinforcement. Finally, we provide transverse reinforcement based on temperature and shrinkage. As per IS 456-2000, clause 26.5.2.1, the minimum amount of transverse reinforcement AST min in millimeter square for unit width of slab is given as follows. AST min is equal to 0.15% of the total section, which is 1000 times H for Fe 250 grade of steel, and AST min is equal to 0.12% of 1000 H for Fe 415 grade of steel. Usually, the transverse reinforcement is provided by non-prestressed reinforcement. The minimum reinforcement is sufficient for the transverse moment due to Poisson's effect and small point loads. For heavy point load, transverse reinforcement need to be computed explicitly. Thus, whatever transverse reinforcement we provide is adequate for any transverse bending due to the Poisson's effect or due to small point loads. If there is a large point load, then we have to explicitly calculate the transverse reinforcement. Next, We are learning this principle from a design example. Design a simply supported precast, prestressed type 2 composite slab for the following data. Width of the slab is 0.3 meters, clear span is equal to 2.9 meters, effective span L is equal to 3.1 meters, thickness of the precast slab is 50 millimeters, thickness of the cast-in slab is 50 millimeters. The grade of concrete in the precast slab is M60, the grade of concrete in the topping slab is M15. Note that the two grades of concrete are different. The topping slab is a linear concrete as compared to the precast portion. The tendons are located at mid depth of the precast slab. The live load is 2 kilonewton per meter square and the load due to floor finish is 1.5 kilonewton per meter square. This problem has been taken from a guidebook titled Partially Precast Composite PSC Slab, authored by Professor A.R. Santakumar, and it has been published by the Building Technology Center of Anna University, Chennai. First, we are calculating the moments, the load per unit area. First, we are calculating the weight of the precast slab. Next, we are calculating the weight of the topping slab. Then, we are calculating the weight of the floor finish. And finally, we are adding the live load. This gives us a total load of 6 kilonewton per meter square of the slab. The total moment MT along the width of the slab is given as the weight times the width times the span square divided by 8. This is the simple expression for a simply supported slab, and substituting the values we get MT is equal to 2.16 kilonewton meters. The individual moments are calculated based on the proportionality of the loads. We can calculate MSW, which is the moment due to self-weight of the precast slab, which comes out to be 0.45 kilonewton meters. M top, the moment due to the weight of the topping slab, comes out again 0.45 kilonewton meters. M finish, which is the moment due to the weight of the floor finish, is equal to 0.54 kilonewton meters, and MLL, moment due to live load, is coming out to be 0.72 kilonewton meters. Thus, once we have calculated MT, we can quickly calculate these individual moments by taking the load proportionality. Next, we are calculating the geometric properties. For the precast section, the cross section area is 300 millimeters times the depth 50 millimeters, which is 15,000 millimeters square. The moment of inertia I1 is equal to 1 by 12 B times depth cube, which comes out to be 3125000 millimeter to the power 4. We are calculating the distance to the extreme fibers CB and CT, which both are 25 millimeters. The section modulus can be calculated as I1 divided by CB or CT, and both of them are equal to 125,000 millimeter cube. For the composite section, since the grade of concrete are different for the precast, prestressed and cast in situ portions, an equivalent or transformed area is calculated. The CIS portion is assigned a reduced width based on the equivalent area factor, which is also called the modular ratio. The equivalent area factor is determined based on the grades of concrete, and we get a value of 0.5. Thus, the composite section is being transformed to an equivalent section with a reduced width of the topping slab, which is 50% of its original value. For the composite transformed section, we are finding out the centroid. We are calculating the area of the top, area of the bottom, the total area, from which we are locating the centroid, which is at a distance of 41.7 millimeters from the bottom. And this is the CGC of the equivalent transformed section. We are calculating the moment of inertia of this equivalent section. First, we are calculating the I of the top part for the axis passing through the CGC. We are calculating I bottom for the bottom part, and then we are adding these two values to get the total I for the composite section. Distance of the extreme fibers is given as 41.7 and 58.3, and the section modulus for the composite transformed section can be calculated by the I divided by the respective Y values, which gives the section moduli. We are calculating the prestress. Since the tendons are located at the mid depth of the precast slab, E is 0 for the precast slab. The value of PE is calculated directly from the following stress profiles. That means PE generates a uniform compressive stress, then the self-weight and the topping load generates a stress profile like this, and finally we have the finished loads and the live load moment, which is acting over the full composite section. From these stress profiles, we can say to avoid tensile stress at the bottom under service conditions, the resultant stress is equated to 0. Once we write an expression of the resultant stress and we equate it to 0, we get an expression of the effective prestress that we need to apply at the precast plank. And from this expression, we can find out the value of PE. In this above expression, the first term inside the bracket corresponds to the precast section. The moments due to self-weight and topping slab are resisted by the precast section alone. The second term inside the bracket corresponds to the equivalent section. The moments due to weight of the floor finish and live load are resisted by the equivalent section. Thus, we are using the principles of a composite section to analyze this composite slab. Substituting the values, we get the value of the prestress as 153816 newtons. Assuming 20% loss, the prestress at transfer P0 is almost equal to 1.2 times PE, which is equal to 184579 newtons. Selecting wires of diameter 7 millimeters and ultimate strength FPK is equal to 1500 MPa, we are calculating the area of prestressing steel. Area of one wire is 38.48 millimeters square. The maximum allowable tension in one wire is equal to 0.8 FPK times AP, which is 46176 newtons. Thus, the number of wires required is equal to 184579, which is the prestressing force at transfer divided by the maximum prestressing force that can be applied in one wire, which gives us a value of 4 wires needed within 300 millimeters. Required pull in each wire is given as the total prestressing force P0 divided by 4, and thus the total prestressing force is equal to P0 equal to 4 times 46145 is equal to 184580 newtons. These values turn out to be close because we have got a value 4 which is very close to the calculated one, 3.99. The effective prestressing force is 80% of the prestressing force at transfer, which comes out to be 147664 newtons. We are checking the stresses at transfer. The compressive strength is 70% of FCK, which is 42 MPa. The allowable compressive stress is 0.44 FCI, which comes out to be 18.5 MPa. For type 2 members, the allowable tensile stress is 3 megapascal. At transfer, we see that for the precast portion, the average stress is minus 12.3 MPa, which is less than the allowable value of 18 MPa. Hence, it is satisfactory for the transfer load case. At mid-span of the precast section, we are including the moment due to self-weight, and there also we find that the stress at the top, which is the higher value, 15.9, is less than the allowable value, and hence this stress profile is acceptable at transfer. After casting of the topping slab at 28 days, the allowable compressive stress is now 0.44 of 60, which is 26.4 MPa, and the allowable tensile stress still remains as 3 MPa. After the casting of the topping slab, we are calculating the stress conditions at the mid-span. We have the force due to the prestressing force and due to the self-weight and topping slab, and these values are coming out to be minus 19.5, which is the higher one, and this is also less than the allowable compressive value. At surface conditions, for the prestressing portion, the allowable compressive stress is 21, the allowable tensile stress is 3, and the expression of the stress at the mid-span for the composite section is given as by that minus PE by A, the prestressing force, then the effect of the self-weight and the topping moment, and the effect of the finishing moment and the live load moment. We are calculating the stresses at the junction. We find out it is minus 17.6, and the stress at the bottom is 0.4 MPa. These values are for the precast portion. For the cast in situ portion, the stress at the top is minus 4.3 MPa, and the stress at the junction is minus 0.6 MPa. And thus, we get the stress profile for the composite section, and we see that most of the stress is concentrated in the precast portion, and here also this value minus 17.6 is less than the allowable compressive stress, and hence the stress profile under service condition is acceptable. We are checking the shear capacity. We are first finding out the shear capacity to be 42 kilonewtons and the shear demand to be 4.2 kilonewtons, and since the shear strength is greater than the demand, the shear capacity is adequate. We are providing some transverse reinforcement as per the minimum requirement, that is 8 mm diameters at 300 mm on center. Thus, this is the final design of the precast plank. We have laid the prestressing steel, we have laid the topping steel, and we have cast the concrete, and finally we get the precast plank for the design forces. Thus, in this module, we covered one-way slabs, and then we studied the analysis and design of one-way slabs. Thank you.